I'm sure you all have heard about the Gaussian function or the normal distribution. In the most popular form, it is written in this form. F of x is 1 over sigma root of 2 pi e to the 1/2 x minus mu divided by sigma all squared. Okay, so that's the normal distribution. The Fourier transform of the normal distribution is the normal distribution. So this is a wonderful thing about the Gaussian function or the normal distribution, that the Fourier transform leaves it almost unchanged. The only difference is that the coefficient in front is 1 over sigma root of 2 pi will change in the transformation. But otherwise, in the x world and in the omega world, these functions look the same. And you know how they look like, right? These are the bell-shaped curves. They look like this, where here is the mean, is mu. That's where the maximum is. If mu is equal to 0, then we get something like a constant times e to the minus a coefficient x square. You see, so we keep the x square, and then this minus 1 over 2 sigma I call a. And so then this is kind of the function we should be looking at. How does a Fourier transformation of an exponential to the minus ax square look like? And then the constants is a separate issue, right? We worry about the constants as they arise. Good, that's what I plan to do. So here in lemma 8.5, I just first solve an integral from 0 to infinity of this function e to the minus omega square b d omega. And I claim that I can integrate this, and the result is root of pi divided by 4b. Now this proof of this lemma is actually really cute. So I call this integral I. Okay, I just give it another name. So here I look at I square, which means I write the product of the two integrals, but I change the names. I call the integration constant x here, right? On the previous page it was called omega. Now I call it x, and I call it y here. Again, previously it was called omega. I don't want to use the same letter because these are different integrals, right? These are different integration variables. But for different letters, I can actually combine this and make it into a double integral e to the minus x square plus y square b, because the exponentials multiply by summing up the exponents. So that's pretty cool. And now the trick is to introduce polar coordinates for this integration. So what I do is I call x to be rho cos theta, and I call y to be rho sine theta, right? We have seen polar coordinates. This is a substitution in the integral, okay? And so then we substitute the integration, and we get that the dx dy becomes rho d theta. If you carry out the substitution, we have done this many times, and then the theta integral here is from 0 to pi over 2. The rho radial integral is from 0 to infinity, and then we get this additional rho from the transformation formula from here. And then also x square plus y square is of course rho square. So this explains the rho square then here in the exponent. But then this becomes a simple integration of an exponential, okay? We have e to the minus rho square b times rho. So this times rho acts as an inner derivative of the differential of e to the minus rho square b. It's not quite that, so the inner derivative would be minus 2 rho b. That's the derivative of the exponent. So I smuggle in a minus 2b, and I divide it out here in the front. Okay. And then the pi over 2 comes from the theta integration, which I can directly do. There's no theta dependence anymore, so it's just a factor pi over 2. So I keep the pi over 2. I keep the minus 1 over 2b, which is then all here. And then the integral can be done. It is now the integral is e to the minus rho square b between 0 and infinity. Subbing in infinity, I get 0. Subbing in 0, I get 1. So then this is the result for I square, which means I is this number. That's a cool trick. Try to solve I directly. You will not be successful. But putting an I square and then using the idea of polar coordinates in the combined space of x and y is rather cute. Perfect. So here we need one more integration of this sort. We take the e to the minus omega square b, but now we multiply it with cosine omega r d omega. And then we get the same factor as before, the root of pi divided by 4b, but now another factor e to the minus r squared divided by 4b. So let's go through this proof as well. Now I call this function I'm interested in g of r. Okay, and the r is the coefficient inside the cosine, where we do not integrate over r, we integrate over omega. So r only appears as a parameter. So what I then do is I differentiate that whole thing by r. So this will be g prime of r. And then I can, if the integrations exist, so this is what we say here, the integral converges uniformly, I can move the derivative inside and then differentiate the whole thing by r. So I only need to differentiate cosine, and the derivative is minus sine with a factor omega coming out. So that's the derivative. And now we take this one and integrate it by parts. All right, here the same formula again for g prime. And now again I want to make the trick that this omega comes from the inner derivative of the exponent. So I extend it by a factor minus 2b, which I then make up here, and one minus sign cancels. And then this would be v prime u, so now I can do integration by parts. The first bit would be v times u between 0 and infinity, and the other bit is v times u prime, so I differentiate again with respect to omega this time. So I get the factor r out of the cosine there. Okay, so now the first bit is 0. If I sub in infinity, then the exponential term gets to 0. If I sub in 0, then the sine term goes to 0. So this is gone. But the other term remains, and I can take the r out of the integration. It is now in the front. And I keep e to the minus omega square b cosine omega r, which is our function g. This is exactly g. So then this is minus r divided by 2p g of r. So we get a differential equation. We get g prime is minus r divided by 2b g. So let's go and solve first order linear differential equations. One method is to use an integrating factor. So we can use an integrating factor e to the r squared divided by 4b. And then we can write down this differential equation here, or that one there, as d by dr. E to the r squared divided by 4p gr is 0. And this can be integrated, so then this whole shebang here would be a constant. And multiplying by e to the minus r squared 4b, we get then this formula here. Okay. Now, what's the constant? The constant we can find by subbing in 0. If we sub in 0, then the cosine of 0 is 1, and we get the integral from before. All right? And then this was pi divided by 4b and a big root around them. Good. Putting the c back into the formula, we get the formula for g of r. All right, so these were just preliminary results. Now we have to come to the Fourier transform of the Gaussian. So the theorem 8.13, starting here, continues on the next page. Here we go. So that's the central formula I'm after. The Fourier transform of e to the minus ax square equals 1 divided by root of 4 pi a, e to the minus omega square divided by 4a. And that's the thing which I wanted to mention. So we have e to the minus something x square, and the Fourier transform has e to the minus something omega square. This is kind of the invariance of the Gaussian function by Fourier transform. So in the x world, it is a Gaussian curve. In the omega world, it is as well. Let's get rid of this. So let's Fourier transform this whole thing. So we take f to be this function. Then the Fourier transform by definition is taking this function, multiplying it with e to the I omega x, and then integrating. And the complex exponential here I write as cosine plus I sine. And then I split it up into two parts, the cosine integral and the sine integral. Now the cosine integral we just did. This is the previous lemma. But the sine integral we didn't do. And here we use an odd-even argument. So this function is even. This function is odd. So the product is odd. And then the symmetric integral from minus to plus infinity will be 0. Ah, cool. So we really only don't need to worry about the cosine term. So then the cosine integral is the formula we had before. We have an additional factor 1 over 2 pi, which we need to carry through. And so then this is exactly what we get from the previous lemma. Hey, and that's done. Now the reverse is then also true if I use the inverse Fourier transform on e to the minus a omega square, then I get 2 pi times 1 over root of 4 pi a e to the minus x square 4a. So you can go back and forth, Fourier transform, inverse Fourier transform. You always get a Gaussian, but the constants change in doing that.